entropy and the second law. How do we use heat to do work? And can we convert all the heat that is available to us to do useful work? The air all around us has internal energy. We know that all matter has internal energy. But then can we make use of it? Can we run an engine using the internal energy from air? This is what we propose. So we have air which possesses internal energy. We take some of that energy in the form of heat and we use it to drive a car. As the car moves, it'll do work on the surrounding air and it'll return the energy back to the air. And then we can drive this forever and we would never need to refuel. The first law says that for energy to be conserved, the heat taken from the air must equal the work which is returned to it. But the first law, therefore, is satisfied. Energy is conserved in this process. So there is nothing in the first law which says that we cannot run an engine using energy from the air. But this sounds much too good to be true. So why will this not work? To understand why we cannot drive an engine using heat from the air, let's try and understand how an engine works. So suppose we have a high temperature heat source. This could be done by burning a fuel in a combustor. And this is at a high temperature, TH. Now, if we want to use this to do useful work, we can take a cylinder filled with gas. We can heat the gas using energy from this combustor. The gas expands and it does work on the surroundings. But eventually, the gas will reach the same temperature as the combustor, TH. At this point, it'll be in a state of equilibrium, which means it's not going to expand any further, and we cannot do any more work. If we want to extract further work from this engine, we have to lower the piston again. Now we could do this if we have another low temperature heat sink. Now typically the atmosphere acts as this heat sink, and this is at a lower temperature, TC. Now we can lose heat from our cylinder to this heat sink. The gas will contract, the piston will be lowered, and this will eventually bring the gas in the cylinder back to a temperature TC. We can now repeat this process, and by alternating between TH and TC, we can operate an engine cycle, and we can keep doing this indefinitely. So why can we not use energy from the air? It's because two temperatures are required to operate an engine. We need a high temperature heat source and a low temperature heat sink. If we have only a heat source, the engine will eventually reach a state of equilibrium and it'll stop working. Once this happens, we must disrupt this equilibrium by switching from the heat source to the heat sink. Now, in a real engine, like an automotive engine, the heat source is the fuel burnt, which generates a high temperature. The heat sink is the surrounding atmosphere, and we reject heat to it when we lose the exhaust from the engine into the surrounding atmosphere. To use heat from the atmosphere, we would need to have another heat sink that is at a lower temperature. And this is the problem, that usually it is not very convenient to try and find another heat sink which is at a lower temperature than the atmosphere. It is possible to do that. So people have designed heat cycles which take heat from the atmosphere and they reject heat to a low temperature, for example, if you have colder ocean water. But this is something you can only use in a limited number of locations. So we know now that not all heat can be converted to work. But is there a property that could tell us how much work we can get from a given amount of heat? Now, this property, if we were to define it, would be a function of the amount of heat, but it also has to be a function of its temperature. So if the temperature of the combustor, for example, was increased, the piston would have gone higher and we could have done more work. So now we have a concept where it is not only the quantity of heat which is important, but there's also a quality of that. The higher the temperature, the better the quality of the heat. So let us postulate that every system has an extensive property which we are going to call entropy. And the entropy of a system changes when there's heat transfer to or from it. The entropy change we are going to define is the magnitude of the heat transferred and divided by the temperature. Now, the lower the entropy change associated with any heat transfer, the more the work that can be done with it. Because the entropy change, the higher the temperature, the lower the entropy change. So high temperature heat is associated with a low entropy change, and that is more useful. So let's see how we would define the entropy change for a system. This is our system. We are adding a small amount of heat, delta Q, to it. The change in entropy, and we shall use S as the symbol for entropy. So the change in entropy, ds, is equal to delta Q by T. Now entropy, we are saying, is an extensive property, which is why we use the uppercase S, and it is a property, so the change in entropy would be ds. T over here, we are going to define is the temperature of the system boundary where the heat crosses. The units of entropy now are going to be that of heat divided by temperature. So the units would be joules per Kelvin. Now note that the internal energy is quite similar to the entropy. So if we had a constant volume system, the change in internal energy would be equal to delta Q. The change in entropy, we are saying, is delta Q divided by T. So entropy is a property which is quite similar to energy. The total change in entropy, which would be the integral ds from 1 to 2, would therefore be the integral from 1 to 2 delta Q by T. Now, before we go further, we're trying to evaluate changes in the entropy. It's useful to remember our definition of a thermal reservoir. So we had defined a thermal reservoir as being a system whose temperature remains constant and uniform despite heat transfer to or from it. And examples of this would be a large mass, so something like the atmosphere, a lake, a combustor, which is burning fuel to keep a constant temperature even while it's supplying heat, would be another example. Or any other very large mass which has a very large thermal mass. So now let's look at the entropy change of a thermal reservoir. Delta S is the integral delta Q divided by T. This is a thermal reservoir. So let's take the temperature outside the integral because the temperature is a constant. This would then simply become Q12 divided by T, where Q12 is the total heat transfer to the thermal reservoir, and T is the temperature of the thermal reservoir. So for a thermal reservoir, the change in entropy simply becomes the heat transferred Q12 divided by the temperature. We could also write this on a rate basis where S dot, which is the rate of change of entropy, would be equal to Q dot, which is the rate of heat transfer divided by the temperature. So Q dot is the rate of heat transfer, the units would be watts. S dot would be the rate of entropy change, and the units of that would be watts per Kelvin. Let us look at heat transfer between two thermal reservoirs. We have a thermal reservoir, A, which is at a temperature T plus delta T. We have another thermal reservoir, B, which is at a temperature T. Now, delta T we assume is positive, so T plus delta T is the higher temperature. So we bring these reservoirs in contact, there'll be heat transfer Q from T plus delta T to T. Now let's calculate the entropy change for the thermal reservoir A. So we'll call that delta SA, and that would be Q divided by T plus delta T. Similarly, the entropy change for B, delta SB, would be equal to Q divided by T. Now, since T plus delta T is greater than T, delta SA would be less than delta SB. Now, entropy reaching B, therefore, is greater than that leaving A. So this additional entropy is coming from nowhere. It is being generated during this heat transfer process. So we can talk about entropy generation, and we'll call that S-gen. And this would be the difference between delta SB and delta SA. Now, in the limit that delta T goes to 0, delta SB would be equal to delta SA. And in that case, there is no entropy generated. S-gen would be equal to 0. So this is a very important observation, that there is no entropy generated when the heat transfer takes place between two thermal reservoirs whose temperatures differ by an infinitesimal amount. S-gen is delta SB minus delta SA. Now suppose instead of generating entropy, we want to destroy entropy. So destroying entropy would mean that S-gen is negative, in which case delta SB would have to be smaller than delta SA. For this to be true, we require that T plus delta T is less than T, or delta T is negative. So in this case, if delta T is negative, the system A is colder than system B. But we have said that heat goes from the colder system A to the hotter system B. And this is not possible because we know that heat transfer is always from the higher temperature to the lower temperature. So therefore, we can say that entropy can be generated, but it cannot be destroyed. Here we have an isolated system, which is a closed, sealed, insulated box with a gas inside. Now suppose we inject a small volume of a hot gas. The hot gas will lose heat to the surroundings, which will heat up, until eventually we reach equilibrium, where the temperature of the gas everywhere is uniform. Now heat diffuses away from the hot region, so we get some heat transfer, delta Q. We know that entropy is generated whenever we have any heat transfer through a finite temperature difference. The entropy that is generated cannot leave the isolated system. It is isolated, which means you cannot transfer anything from inside it to the outside. So if the entropy cannot leave, the system entropy increases. The entropy production stops only when equilibrium is reached. Once equilibrium is reached, the temperature is uniform. And at this point, the entropy must be maximum because it cannot increase any further. We have reached equilibrium. We can therefore say that the entropy of an isolated system increases until it reaches equilibrium, and then it remains constant. the entropy of an isolated system increases. And this happens because heat transfer is from higher temperatures to lower temperatures. Now, this is an observation that cannot be proven from first principles, but it is based on our observation of the universe. That is just how the universe works. So we are going to sum this up in a postulate. And this is what is known as the second law of thermodynamics. The second law says that the entropy of an isolated system will increase until the system reaches a state of equilibrium. The entropy of an isolated system in equilibrium remains constant. We can write this mathematically by saying that ds isolated is greater than 0 for an isolated system that is not in equilibrium. ds for an isolated system is equal to 0, and this is for an isolated system in equilibrium. And ds isolated being less than 0 is not possible for an isolated system because this would mean that the entropy was being destroyed. So again, entropy can be created, but it cannot be destroyed. To summarize, entropy is an extensive property, and we have defined it by saying that ds is equal to delta Q upon T. The change in entropy of a thermal reservoir, delta S, is equal to Q12, which is the heat transferred to the thermal reservoir, divided by T, the temperature of the thermal reservoir. Entropy is created when heat is transferred through a finite temperature difference. Work does not change the entropy of a system. Entropy cannot be destroyed. And the second law states that the entropy of an isolated system increases until it reaches equilibrium, and then it remains constant.